Welcome back to the second lecture video for our Class 15 series of lecture videos. We ended our first video considering the reaction of tert-butyl bromide and water. And so let's look at an energy versus reaction coordinate diagram for this SN1 reaction of tert-butyl bromide and water. So here we go. Right? For our reaction coordinate, we start out with tert-butyl bromide. We have an ocean of water. Our first step in the SN1 reaction is our tert-butyl bromide falls apart. It's our rate limiting step. It has the highest activation energy. We actually prefer a polar protic solvent in our SN1 reactions in order to do this first step. Why? Because the products of this first step, this rate limiting step, are these high energy carbocation and anion intermediates, and a nice polar protic solvent has strong interactions, so it stabilizes these intermediates, and in fact the solvent becomes part of the product. So the oxygen, whose electrons are stabilizing the carbocation, those electrons just add in. And then we do a deprotonation and we get to our tert-butyl alcohol and our H3O plus and Br minus. So since the solvent, water, separates the charged intermediates, that is the carbocation and the bromide anion, and it ends up as part of the product, we refer to this type of reaction as a solvolysis. Now, I don't know, you probably remember that not only halides like chloride, bromide, and iodide are good leaving groups, but sulfonates are too. So here we go. We've got a triflate here. That's a tertiary carbon. Doesn't have to be water. That's our polar protic solvent. We could use methanol. And lo and behold, this methoxy group ends up substituting for our triflate, and we get triflic acid. So we went through an SN1 mechanism in this reaction. I suppose we could think about a case in which we have competing SN1 products. Maybe we throw tert-butyl bromide in a mixture of water and methanol, which are infinitely miscible in each other. We could end up with tert-butyl alcohol and methyl tert-butyl ether at the end of the day, and HBr. We could have a couple of different types of reactions going on. They share the same rate limiting step, which would be, breaking down of our tert-butyl bromide. So the rate is not influenced by water or methanol. The product distribution will vary. Hard to predict. The initial lysis, the heterolysis of the tert-butyl bromide is the rate determining step. Let's talk a little bit about stereochemical consequences. Hopefully this won't take too long, and then we'll go ahead and end this, at least, video. Sometimes charge-separated ion pairs aren't fully separated. Oh, let's pretend we start off with this compound that has one and only one stereocenter, so we know it's chiral. It has a non-superimposable mirror image. Most ideas about the SN1 reaction mechanism is we go through an achiral carbocation intermediate. And so if we start out with this pure stereocenter, we should get racemization. The water should be able to substitute into either the white lobe or the dark shaded lobe on our empty p orbital of our carbocation. And we would expect 50-50. However, what we see is only 40% retains the stereochemistry, and we get an excess, an antimeric excess of the inversion. So that almost looks like SN2. So why is the product not completely racemic? That should be a question mark. And the answer is, well, when we initially break apart, the chloride kind of shields that top face, and it's actually easier for our water molecule to put its electron pair in from the bottom face. So momentarily, as we break up, the chloride kind of shields that top face, and so we get less retention of stereochemistry and more inversion. Like I said, sometimes charged separated solvated iron pairs aren't fully separated. So the upper face may be shielded by closely associated chloride ion. This is kind of a subtle feature of SN1. In general, yes, stereocenters racemize, but they may not racemize completely. So a nice point to consider. And I guess our second video is going to be a little shorter than usual, which is a good thing.